actually he's at least working in Bologna.
Bologna, yes. This is my sixth Central Mediterranean program. So it's a Euro-Mediterranean Center for Climate Change. And we have, it's the first Italian institute that is dedicated to a certain field of research, thematic institute. So concentrating on research on the climate change.
Yeah. Anyway, his main field now is working with operational Mediterranean, model of the Mediterranean ocean model, and data simulation.
Okay, thank you very much. I was I will give a talk because I propose this not because I'm very much involved in this work, but because I thought it could be interesting to see also a different way of solving more or less the same problem. And I was just partly involved. As you can see here, I'm only the fifth total, and especially the first four were really involved very much, more or less equally, and I was a little bit less, and mainly in the implementation of this scheme, not really in the development. In the implementation, then later in the ocean model, not to quantify the wind forcing uncertainty. So this work of quantifying the wind forcing uncertainties was made mainly by the other authors. So I just have to apologize in advance because maybe some things will not be completely clear now to me, but I think they are. But still, I think maybe here there are also better experts on this. And maybe it will not be as long as it was announced, about 1 hour, maybe a little bit less. I'm not sure. So the outline. So I will just say a few words about the forecast uncertainty. So I'm talking about a realistic data simulation system that runs in an operational mode. In the Adriatic Sea, we provide forecasts every day for the state of physical parameters in the Mediterranean Sea. And then I will talk about this Bayesian hierarchical modeling approach to quantify one part of the uncertainty of our system. So that there are many uncertainties. Some are due to the model, and just we don't know exactly what are the model parameters like. Then there are others due to some other parameters. For example, we don't know exactly what is the shortwave radiation. What is the cloud cover, and so on. But also we don't know exactly what is the bottom topography in many areas. And then one of the most important problem parameters is the surface, is the wind force. So there is a surface vector wind, which I here say it's SVW. It's one of the most important sources of the uncertainty in our forecasts. And also in our analysis, because in the ocean we do make forecasts, but equally important are the analysis, because the system we don't really observe it, like the atmosphere, at least the surface. There are many people and they see what is the weather like, but in the ocean we would like also to estimate the state of the system, not only to make short-term forecasts, and by using these methods. And then I will talk about this new method then that is based on this Bayesian hierarchical estimates of the uncertainties in the surface winds. So the Bayes theorem is this well-known equation that says that this presentation is not mine, it's by Nadia Pinardi, so that's why I just want not to change anything inside. So, but just usually we usually use y to be observations, but actually here it's presented as our process that we want to estimate. So y is our model state vector. X now are observations. So what we want to estimate, and we denote this with this brackets with angles this is a distribution of any quantity, and what we want to know is the posterior distribution of the physical variable that we want to estimate given the observations x. And this can be, of course, written in this form using the Bayes theorem, that it is the distribution of data given the background, given the physical variable estimate, times the distribution of the physical variable of interest. And so we call in this, with Bayesian model, we call, this is the data stage. So we have a data stage and we have the prior or the process model stage. So this is all very similar to what we were doing to develop, we are doing actually when we want, starting from the statistical theory, to develop either Kalman filter, Bayesian statistical theory, either by Kalman filter or the minimization cost function. So we would, and this is simply a normalization constant that ensures that this distribution, when it's taken as an integral, becomes 1. But it's very difficult to estimate these terms, that is usually not estimated, but only the first, the top two. So, what is now this Bayesian hierarchical model doing? It's actually applying this, if we have a joint distribution of joint of, let's say, 3 parameters in this case, given the observations, then we can simply, in a sequential way, apply several times this theorem, the Bayes theorem, and get something like this. So we have that this posterior estimate distribution of so variables y, theta, and eta given observations are the distribution of observations given y and theta, multiplying the distribution of the state given eta, and multiplied by distribution of theta and distribution of eta. Now, I think this is, here we assume also that theta and eta are independent, otherwise it has to be a joint distribution of theta and eta. So now this is actually this theta is the probability distribution for errors of the data. So this is what we would call actually eta in the Kalman filter. So that would be the error, which would have some probability distribution. And eta would be the probability distribution of parameters of our process model. So that would be...
What is the difference between eta and y?
Eta and y. Okay, so I think it's... there is another... So I would rewrite this, because I was also a bit... not sure with this equation, but I think that. So if we have our, for example, I write it a little bit differently than there. Maybe it's now it's all reversed here. Now, if you have, this is our actually physical variable that we want to estimate, has a distribution, a certain distribution. Now, what we want to get is this is following the paper by Ralph here now. What we want is W theta d. So I'm writing like this, theta p, let's call it, given observations d. Okay, so this is our physical variable of interest. We have unknown errors of the parameters of the process model. Sorry, of the process model and of the data model. So these are our uncertainties, the distribution of parameters of our data and of our model. And we want to know the probability of all of these given the observations. So we want to know, for example, if we have, now let's explain it maybe by, so if we have our wind. So this would be the distribution of the errors of the wind observations, which can be Gaussian but can be very general. We don't give any assumption in advance about what can it be at this stage. And this can be, so we can also have some model of the wind, and then predict that wind. And this would be the error distribution of that, of parameters of the error distribution of this wind, which is always this W. So it's, I think it's, somehow it's similar of what we do, but the difference is now we divide this, we add new parameters into our state estimate. So it's not only this W, but we also have some other parameters that are known. That are, for example, parameters. If you have a model, then we have certain parameters in that model that are unknown, and we also put these parameters into this term here. So we make larger our state that we want to estimate than just the physical parameter that we want to get. Or we also want to estimate the parameters of the model, not only the state. So that becomes bigger. Now this becomes, of course, very complicated if you have it like this. But then we make it proportional to actually. So what we have here is, first of all, is I'm just going to check. Okay. So we have the given data given the process, the physical variable, and then we have also the parameters of the errors of the error distribution of this data. So this would be like we had in Kalman filter. We would call it. I don't remember now. Nu. So it's nu. So this would be when we, for example, we make the mapping from some modeled velocity to observed velocity. We have, this would be the errors due to the mapping. So we have some, because this is something that we would call also representativity error in our system. So that we don't observe exactly what we model. So that would be this, this theta d would have this distribution describing this, that we don't observe the same thing as what we model. At least there will be observations are usually not positioned at the same point where we have model variables. So it can be only interpolation in space, but it can be also more complicated. And then we have the next is multiplying comes out given theta process. So here we have our variable, and this would be actually what we describe in our B matrix sometimes. But this is not anymore. These are errors that, if they are Gaussian, it's sufficient to know the mean value and the second moment, which is actually the covariance of errors. But here we don't do it. I mean, this is really, we multiply the full distributions. So it's like, I think you had this also in the particle filter lecture. I saw there was a lecture on particle filter. So we are not anymore limited to the Gaussian assumption, but we simply multiply the full distributions of parameters. And then there will be, of course, what has to remain is this. Then we have theta d and theta b. And joint distribution of these parameters, unknown parameters of. So in this case, we also assume, and we will assume always that they are independent. So that's the model, the process model stage and the data. The data stage are independent, so also the errors are independent. This is exactly what we assume always when we develop Kalman filter or also other the variation.
Yeah, so let's see if I understand theta p. So that's something like, say, an error in a turbulence scheme.
Yes, that could be an error in turbulence scheme. It can be error in any parameter we want.
Yeah.
Actually, it's more general. So it can be even in the Coriolis term. You can say, okay, maybe we don't know very well the Coriolis term. F is unknown, and we can, by having lots of data, we may try to estimate F statistically. So it's a more general. Any parameter in the model can be part of this theta. So it's not only that we know that is completely unknown, but any parameter that appears in the model. Also the discretization. Maybe we don't know exactly what is the distance between grid points. Suppose that we can, if we have enough data, in principle we could have some estimate of it. In fact, from the statistical point of view, nothing is perfectly known. So everything is actually has some uncertainty in it. Okay, so I hope this is because I think this is the most important part of it, and then it becomes more clear how we do this. Okay, so there are these building blocks. So there is first you have to define this data stage distribution, and this is so you have to quantify somehow this uncertainty in the observations. So you can simply say, for example, as we do in our applications in the variational or Kalman filter, that observations have some kind of Gaussian distribution and that they are independent. But you can also assume some dependency in these errors, so it's not really limited by any of that. But this is typically it's modeled as a quite simple distributions. Then we have this process model stage distribution. This is our prior. So this is some uncertainty in how we connected to the knowledge of physical process that we want to. So here, the idea behind all of this is to try to use simplified models and a large number of simulations. So we have models that have parameters with high uncertainties, or even models are not very, because the models are not very accurate. But we provide, so they are not anymore deterministic, but we know something about the process, specify something by some simplified physical relationships about the process, but there is a certain degree of uncertainty, and we accept that in advance. So we say, okay, our results are quite uncertain, so we will use data to try to estimate the whole distribution of solutions that come from that model. And then we also have to specify these parameter distributions, so how this theta v and theta p are, so this is, they are connected both to the model and the data distribution. So of course theta p is connected to the model and theta v to the. So finally we would like to build this posterior distribution, and this is done by using the Markov chain Monte Carlo methods. So by using the sequential sampling, by trying to always sample in areas which have the highest probability, and in particular this gives sample which is kind of well, it's a recent scheme, but it belongs to this kind of metropolis and Hastings algorithms for sampling. So also we can calculate the mean of the posterior, and we can call it summary, and the standard deviation is called spread. So this is somehow some, let's say, how to say, condensed way of displaying results. So what we have in the Mediterranean, so how we have, this is our domain of our model, and you can see not very, you can't see very well here, but actually there are winds, and there are ECMWF winds in red, and on the grid of the output of the ECMWF model, which is at 50 kilometers, half a degree. And we can see that from every 6 hours we have some observations, but not every time. For example, at 12 there were no observations. At 6 then we had only a very small area, while in these two time steps at 6, at 0 there was a small area, at 6 and at 12 we had this small area. Here it was only, this area was captured by the satellite.
And the rest, there's also arrows over the rest.
Yes, the rest is ECMWF analysis. And this is where they had the quick-scat data. So ECMWF simulates the quick-scat data also. But we were not very satisfied about how they do that. And this is in other times we can have quite good coverage. This is a satellite that is a radar that has some area, a spot that can simulate and gives sufficiently accurate observations at a resolution of about 25 to 50 kilometers in horizontal. So that's, but it has compared to in situ data, then the observations are quite accurate. So there are some tuning on these parameters. What it measures is actually the friction, the wind stress at the surface, and then it is assumed that the velocities of the ocean is 0, which is actually the assumption, and that the vertical profile is neutral, so you can easily close and estimate the wind at 10 meters height, the same wind that you can get from other parameters. So there are some assumptions in getting these winds. I mean, these are not pure observations from the satellite. What they estimate actually the surface roughness, and from the surface roughness you can deduce the wind speed and direction.
So do they assimilate the retrieved winds in ECMWF, or do they assimilate the surface roughness?
I think winds. I think that winds.
Yeah, I know
actually,
that's what the
that
US
would be more
do.
correct, because that's good to use the wind stress and then to adjust the wind stress. And for example, for us, it could be better to have wind stress, because we anyway use the wind stress and not for the ocean model, not the wind. So it's somehow 2 times you go to the wind and then go back.
Putting more arrows there.
Yes, and then you correlate things. Okay, this is why it is not really, we think it is not really the best what is done at the ECMWF. So these are, I don't have here, but it's, okay, so it's along some lines, the kinetic energy of the winds is calculating and put in comparison to the scale in space, so going from 1,000 to 50 kilometers, which is the resolution of satellite observations that are then processed. And we can see that the energy, of course, drops by the reduced horizontal scale, but, and this is for different years. This is from 2000 till 2008, but this drop is much slower than what is given by the ECMWF. Actually, the ECMWF analysis, these are ECMWF analysis that also simulate this data. These analyses have, after probably about, even from 1,000, but also from 500 kilometers, a significantly faster drop in the energy at smaller scales. So, and that gets better, of course, by increasing the resolution, because in these years the operational model increased the resolution. So here it was about, I think, 2 times higher than it is now. So it was about 30 kilometers, and now it's 15 kilometers approximately. But still, there is a huge difference between the energy at the smallest scales and what the ECWF can produce. Well, here's the theoretical line, which is in this. This is not a linear scaling here. So the line of k minus second, that should be theoretically is going approximately like this. So this is really not the noise, observational noise or uncertainty satellites, but this really goes well along the theoretical line, what the satellites observe. I'm sorry, this is not really visible. There is a very, very thin dashed line. Very thin.
So is the ECMWF's inability to resolve the smaller scales due to the outer loop in the data simulation?
I don't know. I think the model already is not able, and they had some problems. That I saw there is a report which says in which they tried to add some noise on the small scale in order to achieve this higher energy at small scales. So they are aware of this problem, and probably yes, they simply filter out the information that exists in satellite data. And in the Mediterranean, the Rossby radius of deformation is only 10 to 20 kilometers. That's similar like in the Nordic seas. And this, so the input of energy at these scales is very important. So this missing energy is actually important. There is some missing of the energy at shorter scales, if enforced by the analysis from DCWF. And this has been actually found in many other studies also that use this quick scat. So it's not only CWF, but also most of the atmospheric models, these global models, have this problem. Here maybe there is some uncertainty is increased, so maybe this tail is not really good, maybe there's already some noise in the data. But at least up to somehow here, some doesn't seem too bad. And there is a little difference from year to year, but here the difference probably can be explained by the increased resolution of the ECMWF model, so that is able to resolve, or maybe the data simulation loop, the 40 bar, which is run now at high resolution, so can take the information from the quick scat.
Do you think this is specific to Mediterranean Sea or the open ocean?
Yes, as I said, there are other studies that show this similar in other areas. I don't know, is it because in the Mediterranean, yes, you have many of these mountains and it's all closed, but is it in the open ocean? I don't know.
I think it's probably numerics, isn't it? I mean,
it is numerics.
The grid is 50k, and the numerical analysts would say you're not going to get realistic energy representation below about 250. They'd say about 5 to 10 grid cells.
Yes, yes, that's quite more, because I think it's the drop starts quite almost even 1,000.
Well, cautious numerical analysts say 10 grid cells.
Yes.
So what is the grid space?
The grid space, here it's going from, I'm sorry, it's not really visible. This is 1,000 kilometers, 500.
No, but the resolution
in this WF, I don't know exactly what is here. Here it was about 30 kilometers. That's in the last, I think, 3 years of this comparison. They were about 50 to 30, I don't know exactly, but about twice as it is now. Now it's, I think this year they went down to 15 kilometers. Okay, of course they are not, for them this is not the most important parameter, prognostic parameter, or even, so what they want is predict the precipitation of strong winds in some peaks, but not really small energies. Maybe that's the reason. They simply don't consider this as an important parameter and don't adjust the parameters in their data simulation scheme or in their model to get this. That would be awesome. Okay, so how now we can proceed? So we have two sources of data actually. One source is QuickScat, which is in black, and the other source is this red that are the ECWF wind estimates. So we have U and V components of the wind given by the QuickScat, by the satellite, and by the ECWF. So we assume that they both are beta. So that we have two sets of beta that give a different estimate, each source of beta. If you don't assimilate anything, we only have ECWF. That's what we do now with an deterministic model. So we assume that the only data is ECWF, and there is no uncertainty in that. But as we have both quick scattered ECWF, we would like to build a new estimate that would include the uncertainty inside. And then we have a very simple model for the wind. So we assume that we also know the pressure, and we can get the pressure from the ECWF analysis. Now the assumption is that the pressure estimate is much better than the wind estimate. Because pressure, we have many more in situ stations. We can have, especially in the Mediterranean, there are many islands or maybe ships, and so we can have lots of estimates. And then pressure, we know that is a smoothly varying function, so it's not, it doesn't change so abruptly like the wind. So that's another advantage. So we know that this parameter somehow, pressure, is something that is a parameter, one of these theta parameters, now becomes one of these theta p parameters that are here. That is now specified with more, we have more confidence into pressure than in winds. So that's the idea behind that. And then we can simply form the simplest equation for the dependence change with time of no, sorry. So okay, we then assume that there is a balance between the pressure gradient term, the Coriolis term, and the friction term. So we assume that we can diagnostically estimate the wind from this balance, which is a very simple balance, but it's used for many years in meteorology, especially before the computers, to estimate the winds from the pressure fields. So you can assume that your actually is, and this would say that minus, it's plus Fu is actually a proportional balance with minus 1 over rho 0, which is a constant, and delta P over delta 1. And then we have the other term is, I don't remember now exactly, but it should be minus some gamma times, now I don't remember, is it velocity, speed, so it could be the model. I'm not sure if this is exactly the form, maybe there is a quadratic term or something, but it's more or less that we say that as a first approximation we can say there is a geostrophic balance, but near the surface it must be also the friction, which would change a bit the wind at the surface, over the surface of the ocean. And so this is simply can be written in the following way. So we can write that our, and that's the same thing then for the v component of the velocity. So we have either the u component and v component of velocity. We can form the same equation where the first approximation is the Coriolis, and then we have also the friction term. And then we can substitute that v over there. So it's probably v squared, then it's easier. Or no, I don't know. So it's we can, or maybe it's just minus gamma times u. Maybe that's simpler. So it could be.
It's a y equation.
Sorry.
It's a y equation.
Oh, that's right. Then it should be. That's right. I don't. I'm not sure. Anyway, if you then substitute here the first order approximation that u is equal to 1 over rho 0 f delta p over delta y, we can put it into the other equation, and then we can actually rearrange the two equations so that u and y depend only on the horizontal gradient of pressure. So this would be the Coriolis, and this would be this friction term. But I'm not sure. I don't remember now exactly the first equation. So, but it can easily you can easily come to this. And then we can put here we can rewrite this that at the time step t, u and v are functions of p, in a way that this v simply now means the horizontal differentiation, and which is a simple field differencing in space. And here we have these parameters theta, uy, ux, vx, and vy, where these parameters are actually these constants. As we say now, we know that this is f quite accurately. So we know that what is the value for f for the Coriolis parameter. We may also estimate quite accurately rho 0, but we don't know what is this gamma. This gamma is quite unknown parameter. So there are some estimates, but they are very rough estimates. So actually all of these parameters have a higher level of uncertainty. And so these parameters now will have to be estimated together with u and v. So all these theta parameters. So we assume that the distance between the points is well known. So yes.
It seems like what you've done here is simply to take the time derivative of those equations about.
That's right.
So there is in fact a time, I mean, before coming.
No, I think this is just index, saying that
okay.
t, we have this dependency plus some uncertainty, also correlated to this physical parameter, but also these have uncertainties. So, okay, here it is. It was actually like this. I'm sorry, I didn't know that it was on this next slide. So here are these equations, even with the term that describes the temporal change, and then we can actually rewrite them even in this case completely by we can simply have, if p is known, we have simply a set of two linear equations with two unknowns, u and v. So we can rearrange them. So in the first case, we can assume that there is a balance actually between, so that we can diagnose u and v directly from p. But in the second term, we must also, if we maintain all the terms in the upper two equations, we must know what is the derivative in time of pressure, and also of u and v. So that would be, but this, we can always assume that these terms are smaller and are not important, so we can simply add this noise, so we can errors that are due to this, that we remove terms from the equations. So we can make a simpler model. So in our case, we use only the first, because also the second choice didn't give any better results, and it was just more complicated. So in fact, it is well known that there is a quite high degree of balance between the pressure and velocity at the surface of the sea.
So this is surface pressure and 10 meter winds.
This is sea level pressure, yes, and the winds are, well, 10 meters. So it's assumed that it's all neutral, so that it's actually the wind at the surface. So somewhere we don't specify, that should be 10 meter wind, yes. We simply, because the ECWF provides 10 meter wind, and also QuickSCAD gives the meter set estimate of the wind at 10 meters. Right. Okay, now we can simply make finite, just discretize these equations, where P is now this spatial derivative in y direction and in x direction, and so we can rewrite these equations in this following form. And now we can specify, we have to specify this theta, that we assume they are random parameters, so they are just stochastic parameters, and that we want to estimate. So actually, we have to start from something. So we make a first guess estimate, and that is that they are Gaussian with this specification of the mean and the variance. And this is actually not necessary to be Gaussian. We can put any of the distributions, but this is just to start with something. Later they will become something else. They will not be anymore Gaussian once we start with experiments. And then also we assume that P can be something, some mu, and then some of practically there are some structure functions that do not depend on time, and then we have time-dependent intensities of this structure function. So this is like an EOF decomposition of P. This is done because this P becomes very large, and it becomes the bottleneck of this computations. So we reduce the number of free modes in this system.
Is this P the pressure?
P is the pressure, yes.
So when you use so this is going to, and this comes from the CNWF.
This is the pressure that comes from this CNWF.
So when you use the Q-SCAT data,
yes,
you are using uncertainty coming from the CWM already there. Right?
That's right. That's an assumption in the system that they are independent, but they are not. So that's one important assumption. That's true.
And then you use it twice when you use the ECNWF.
That's right.
data.
Yes.
So you can mix.
Yes. I fully agree. But it was somehow it was not really taken into account because it then becomes very complicated to take, and then it was simply neglected. But maybe if you think about scales, if ECNWF is not able to really extract some information at these smaller scales, then if you are going to change mainly smaller scales, then maybe this can be assumed. So this is an important assumption. I had the same comment when we were discussing this, but then it was not possible to make it dependent.
And if you choose a prior for P?
Yes, we choose the prior for P is actually from ECNWF, is given by ECNWF analysis. So that's the here as I said before, we think that our confidence or our certainty about P is much bigger than about U and V. So we think that ECNWF gives analysis of pressure that are much more accurate than of the wind components. For different reasons. Of course, this is also scalar function, so maybe it's easier to get it, to estimate it. And then we know that it is smooth, and that we have many more in situ observations of the pressure, of the surface pressure.
What's mu?
Mu is, well, it's just some constant, which is actually, we just decompose in time the pressure. If you have some 1 month of pressure fields, or I know 1 season of pressure fields, we just decompose them by some kind of, we subtract the mean, and then the rest we make an EOF decomposition, or some other decomposition that is, well, gives some approximation of phi. And then we use only 20 EOFs, and that reduces significantly the size of this state vector. Because the size here is, I think, for pressure is about, so it could be 100 by, let's say, 2,500. So instead of 2,500, we have the dimension becomes 20, which is still we are still able to run with this large number of simulations. So here are some results. So this is all put now into this Markov chain Monte Carlo scheme, and there are about I think about 100,000 iterations. So we have 100,000 samples. So the first, I think, 10,000 or 20,000 are just dropped, and then just the last are kept, something like 8,000 samples are kept. But this is now easy to make so many samples because the field has a small dimension, because it's a two-dimensional field on a coarse grid, which is 50 kilometers. And these are estimates for these parameters, which are actually a bit different than what one would expect. So if you think, I don't know, if this theta u wave y, let's say the first, which would be this one, would have the size of f divided by rho 0 f squared plus gamma squared. If you assume this gamma is 0, negligible, then this would give, I calculated something about 7,000, 7,500. But what we get is here are actually quite smaller values in both cases. So it's smaller, so this seems that this gamma is very large. So this can be explained in two ways, I think. Either the friction is very important, which is not exactly what it can be. Maybe the friction should be about 10, I think maximum 20%, not the half of the as strong to have this strong signal. But the other possibility is because we have in Mediterranean, it's all having these mountains and around, so there is lots of channeling of the flow of wind, and you can have many effects of the wind that are not described by this model. So that these parameters, we estimate them, but there is quite some uncertainty. So simply the model is inaccurate. But then we put processes that we don't see in the model into these parameters. So that could also happen. I'm not sure. But they are, in fact, quite smaller than I would expect from simple scale analysis of how important is the Coriolis term and how much important is friction. Okay, but these are the differences here. So we have when without any quick spell data, so using only ECWF data, we get a very narrow spread. So we have almost the same every this member of this ensemble big. These are, for example, this is the number of ensemble members or members of 10 by 10 to the 4th. So we have 40,000 are really here, and there is a very small spread in values. But when we add quick
so that just means that in the model, in ECWF model,
yes,
that equation is very accurate.
I'm not sure, because this value is less than what I would expect actually. I'm not sure that, because if gamma were small, then this would be 7,500, the minimum, and even larger value, depending on rho 0, which is about 1.2, 1.4, the density of the air is. And but here the values are actually quite small, so they're about 5,000. So that means that the friction is very important, but it's I'm not sure. I don't know exactly is it even the case. I mean, would it really show that it's like this? I don't know.
Yeah, are these all at the initial time, and you've taken them all for like a month's period, or are these?
No, this is a single day,
Okay.
single time step. So we have lots of iterations by the Monte Carlo method, and they give different estimates.
Yeah,
And
it's
these
just really
estimates
surprising.
are all they're grouped, or there is a very narrow spread.
Yeah, it's very surprising that the spread is that narrow.
Yes, but when we add actually quick scat data, then it becomes very wide.
Yeah,
So
and it's interesting because that sort of goes against the theoretical assumptions of a Kalman filter, where you guarantee to reduce spread if you introduce any observational data set,
That's true.
no matter how bad that observational data set is.
Yes. Why could it be?
Because
Yes, but
that's not an attractive proposal for an inference. I mean, that's a restriction of the Kalman filter that you wouldn't
Yes.
want to have in reality.
That's right.
Yes.
Yeah.
But that's,
Yes.
that's true. When you, yes, this is just, okay, understand. And it's interesting. But in the end, it's, when it combines the two, the quickscut and eSIM-WF, it has a smaller spread where it has data, quickscut data, but larger spread where it doesn't. But when there are no quickscut data, it doesn't know anything about, so it has only one truth, or one model, and that model is consistent with itself, and it gives a more narrow spread. So it's simply, by adding more knowledge, we get, it's true, we get more uncertainty in the results, but simply because this is more correct, and this was probably a less correct assumption about the process. I think can be explained maybe like that. Okay, and that's very interesting. Now it becomes, it was quite Gaussian-like, but now it becomes much different. So it's a very complex structure. This is when instead of giving the freedom to propose these parameters, we fix the parameter to have the value f. So to be able to be exactly the Coriolis parameter. Sorry, here. This is Vx and Uy. And then, but then still, and give some uncertainty on this Coriolis parameter, so we can see how this estimates then say that this parameter f is actually becomes uncertain. So there is some because the model is not correct. So we make a too strong assumption on the accuracy of this term. So if we say that in this term we can neglect gamma, and here, and also here and here. So we can simply neglect the gamma in the saying that gamma is much smaller than f. You can see then of course the mean, so in this special experiment, the mean becomes more or less the Coriolis parameter. This is 1 to the times 10 to minus 4. So that's the Coriolis parameter, and this one is about 0. So we also assume that gamma is 0 with some uncertainty. This becomes, this says that both of these assumptions are uncertain, actually. So it's not really, doesn't say that f is not accurate, but that our assumption that this theta equals f is an assumption that has certain uncertainty inside. This was just an experiment to test if this system is able to test our hypothesis. Now this is, so these are some realizations which are not really visible. I'm sorry, really. Okay, we have, so this is the eSIM-WF field. This is the quickscut field. And here it should be without data. There is no data in this day at this time. And this is the mean value of the Vgen, which is actually of this posterior estimate, which is not very visible, I'm sorry, but it's very similar to eSIM-WF. But there is a strong uncertainty. So these vectors have a spread that is quite large. When we have the data from quickscut, and we have eSIM-WF again, the mean is somewhere between the two. Is it really visible? But here also the spread is much smaller. So as you said, the Kalman filter is the same thing. So once you have the data, you reduce the uncertainty actually. So you have so these are different realizations plotted one over the other. And here they really show bigger spread, and here they show a very, very narrow spread. So by simulating also quickscut data, we narrow the solution to a certain value. So it's also interesting that when the wind is strong, eSIM-WF is doing quite well. So the spread is small, but when it's weak wind, then the direction can be very different. So we could have a very large spread of the solution. So, and that is actually quite possible because when the wind is very weak, then also this geostrophic balance can be quite inaccurate. I mean, simply the wind is not the wind due to the pressure gradient. Okay, so this is how this now looks like. So the posterior has now so the Quick cut is again this green, and this is now what this posterior has as the energy spread. So it's very similar to what the Quick cut data give. So this is what was given by this in WF. So we are able to actually increase the or they are actually, I didn't work with this. We're able to increase the energy at a smaller scales by reassimilating this Quick cut data. And then they would take, what we did, we would take, because we cannot make many analyses, we took only 10 analyses. So we made a random sampling from this, and then we can get the energy that can differ quite a lot from what is the estimate from 80,000 members. But if you have only 10, this can be some error. But nevertheless, we made this random sampling from that posterior. And this is the same thing when Quick cut is assimilated and when it is not assimilated. Let's see the result here. Okay, but then it simply says that with Quick cut you managed to bring this closer than it was given initially by ECWF, but if you don't have Quick cut data, you just follow ECWF energy. Okay, this is the spread of these 10 members. So we can see that in different areas, but actually that's here it's more visible, I think, should be at least, yes. So when we have stronger winds, we have a smaller spread, at least in relative terms, but here we have very weak wind, this direction can be in any, you can have any direction, so it's okay, now I think Niels said that he would talk about the data simulation cycle and how it's implemented operational, but I would just like to say 2 words about how we do it. So we do every day we make the forecast, but we do analysis only once a week because the processes in the ocean are slow, and actually we have some problems of data pre-processing. So to get the largest number of observations, we actually do once a week the analysis, so with the previous data from the previous 2 weeks. So we assimilate we assimilate 2 times the observations from 2 weeks before, but starting always from 14 days before. So we never assimilate one observation 2 times actually, but we take it every week, once a week we go backwards 14 days in time and then redo the analysis. So assuming that these observations from 2 weeks before have an influence on the current state. And that's because processes are slower, that helps, that gives a better forecasts after. And then we run 10 days forecast. And then in the following days we don't do analysis anymore, but in this we make short-term simulations with analyzed fields, atmospheric fields from this in WF, and then make every day 10 days forecast. So this is our cycle of the forecasting. Okay, and just this what we did here was to add 10. We have 10 members that assimilate. That's like ECWF is doing the 40-var scheme now. So we have 10 members which just do the same cycle, but independently. Each member is doing its own. And these 10 members are now forced by a random sample from this posterior distribution we had before. Okay, these are some results. This is the initial condition spread. And we can see this is in sea surface temperature and sea surface height. So, well, this is now difficult to say, but In any case, we know that these are the areas that are dynamically more complex. There are many small eddies here and here, and also here there are currents that are very unstable close to the coast. So we can see that this how to say, uncertainty that we put by making, so this is, when we run the forecast, we are simulated in 10 different systems, and now here is the spread of these analyses. These are actually the analysis, 10 analyses and their spread. And you can see also the spread on the sea surface height. Now I don't know exactly here, probably it's not really correlated to dynamics, but it's more maybe some wind with cooling. It's very shallow, so we get some larger scale effects. But in these areas, there are definitely dynamic effects due to the different input of energy or different forcing at these scales. So this is initial, and then in the sea level, this is after 10 days. So we can see that actually after 10 days, these initial disturbances, so we can just run analysis, and we can see that they grow, actually, the differences between different forecasts after 10 days grow. So we can estimate some, say that here we estimate some uncertainty, well, the uncertainty is larger. Okay, maybe I could... Okay, this is also in vertical. We have more or less where we would expect that the uncertainty is the large that is near the front lines, which are, this is the vertical section with the density field, and we can see that the largest standard deviation between different 10 days forecast is where we have the highest front line. So I think this is reasonable because obvious in somehow, because if you have a small error in position on the front, you will have having a high gradient. By using this measure, you can see that there is a larger difference. I mean, so if I make a phase error somewhere here, the RMS or standard deviation will be relatively small because there is a small gradient. Here, if I make a small phase error, I will have much larger error. Measured in this way. I mean, it depends how we measure it. But so these are different members. They are very similar, but you can see that there are differences. For example, this one has some eddies that are going like this, and this one is a bit different, and so on. So it's also here we were studying the dense water uncertainties. These are the waters. If they are dense enough, there will be deep convection. So this is the area of the deep convection of these isolines that are quite similar, but they are different in each realization, slightly different. And this is an interesting thing that comes out, and we think this is really because we have a small, this input of uncertainties at a small scale, not at a large. So we could also use the ECWF ensemble. But the problem is that ECWF ensemble puts uncertainties on the large scales and not on the small scales. So the reaction of the ocean is really mostly is the barotropic. If you have just a large scale change in the wind, then you would just have it's like a lake that oscillates because of that changes in larger scales. But if you also add the small scale uncertainties, then you would change the position and the shape of the eddies that define surface currents. And these large scale oscillations, they don't define any because they are simply fast barotropic oscillations. They don't define currents. And so if we have here we plotted the different members' trajectories, and we can see that actually the ECWF all trajectories go more or less in the same way. But with BHN, they are very different. One goes like this, they can go even like this, or spread like this. So this is really because, and this is for us is an important application. Many important applications actually require surface currents. That's one of the most important prognostic parameters. And for different applications, we would like to be able to predict the trajectories, but also to say what is the uncertainty in the prediction of where the trajectory would go. So this shows that actually these small scales, how they are important. And if we perturb with the small scales, we will get these small I'm sorry, it was a bit longer than I thought I had it here. Okay, this is also the vertical background error covariances estimated by this method, by the BHM spread. This is the RMS of innovations, and for temperature and salinity, that's quite similar, at least in shape, but the values are not exactly the same. So that's, but position is more or less the same, because again, this is actually the thermocline, and at the thermocline we have, where is the thermocline, we know that there will be the largest error. So we can also see that. So again, we have the largest gradient in the density field. There were several experiments, and this is, for example, how these members look like. This is in the Gulf of Limes, and we can see that these are the members from the ECWF forecasts, and these are the members of the wind. So we add this wind only to the deterministic forecast of this uncertainty, the deterministic forecast of the ECWF. And here are the members from here. These actually have a smaller spread, but this spread is more on a small scale, so that's the big difference. Here the spread is on the larger scale. And this seems to have a bigger impact on, for example, trajectories. This is, let's get this. So this is 10 days forecast. Okay, this is the spread when we perturb only the initial condition by our estimate of the B matrix of background error covariances. So we get actually something that is quite similar, but we have a more spread in different areas. So this tells us, this is completely what we call this climatological. So we perturb the initial condition with our climatological estimate of background error covariances. And then we run the model for 10 days and the forecast with 10 members. And this is the spread. And this is the spread only due to the wind. So we can see that actually this wind gives us only a part of the answer. And when we assimilate, when we compare this to the actual errors, innovations of these forecasts, we get better result with this one than with this one. So that tells us that this wind, the estimate of errors from the wind are only part of the answer. That the errors are from many other things, not only the wind, at least not in this small space. Okay, and then I'll just, there are these papers, and actually both are already accepted, and I think they can be downloaded from the Portable Journal. And the first one explains the methodology, the second is about the implementation. That's it. Thank you.
One question, so if you want to run this operation, I mean, you have large gaps in this mixed gas
that's right. That's right, but so we have...
So how do you do, I mean, that means that you are reinforced with data which is very innovative. Sometimes you have already smooth center data, sometimes you have a high...
Yes,
does that give any...
That we can't... so this is actually... Okay, so that's... I think this one. So when we don't have quick-scat data, we have much larger spread. But when we have quick-scat data, then we have a smaller spread. But that's correct, because in that case, when we have quick-scat data, we are more confident to the
What do you mean by this method? You can still have this small-scale structure to this.
Yes, but in the end, we give forcing that is now combines both quick-scat and ECWF. When we don't have a quick-scat, then we only increase the spread. So we still have ECWF, but with some larger spread.
And you sort of add the small scales in this case.
In this case, yes, probably.
In a random way, you add small scales.
In a random way, which is consistent with the statistics of differences between the fields. Yes.
Okay. More questions?
So this is another way, for example, of thinking about how to simulate data if you can explain your process simply enough with some computational efficient way, because it's necessary to make many integrations.